Good day, ASs. We're going to start chapter 13 today, and this is our last week before holidays. So let's get into this new topic for this week. I'm going to teach quite a bit, so this is going to be a fairly lengthy video, but this is going to give you a good opportunity to look into our new topic of differentiation. So let's start with what we have here. This is a Cartesian plane, an x and y axis, which you are already familiar with, and it's got a straight line on it. Now we can say that this line is y is equal to, let's make it a half x plus 3, and another way that I could express this is that this is the function, a half x plus 3. And if I said to you, what is the gradient of this function, you'd say straight away to me, I'm sure, that it is a half, because that's the value in front of the x. Okay, and we can easily measure this gradient, what we normally do, and you've done this many times before. If I find any 2 points on the graph, I can find the change in y over the change in x, and I can work out the graph, and we'd expect that that value would come out to a half in this case. Now that's a fairly normal question, and I'm sure nothing surprised you when I gave you this. Okay, but let's have a look at something else now. So I'm going to move across here, and here is another graph or function. Okay, I'm going to call this one f of x is equal to x squared minus 2. Now if I say to you, what is the gradient of this graph, okay, or this function, you'd probably go, well, I'm not actually sure what the gradient is, okay, or how would we measure that? Well, the thing is, while we couldn't measure the gradient, something we could do is we could measure maybe the average gradient between certain points. So let's find 1 or 2 points on this graph quickly. So I'm going to make just a table of x and y values quickly. Let's do that over here. Here we go, x and y. And let's put in x is 0, then we know y to be minus 2. If x is 1, we know it is minus 1. If x is 2, it's 4 minus 2, which is 2. And if x is 3, then we've got 9 minus 2, which is 7. So these are all points on the graph. We could do some negative ones as well, but I don't really need those right now. So we know that the 0 minus 2 point would be here. The 1 minus 1 point might be here. The 2 and 2 point might be here. And the 3 and 7 point would be a bit higher up there. Okay, all right. So we've got a series of points. Okay, let's say we wanted to work out what the average gradient is over here. Okay, that's between these first 2 points. Well, the change in y would be minus 1 minus minus 2, which would be minus 1 plus 2, which would be 1. And the gradient for the x would be 1 minus 0, which is 1. So this gradient over here, the average gradient, would be a gradient of 1. But if I took these 2 points over here, which is the 2 and the 1, and I did the same thing, I'd say the change in y is 2 minus minus 1, which is 3, over the 2 minus 1, which is still 1, and the gradient is 3. And from the graph, you can see that that makes sense, because the first gradient was not quite as steep as the second gradient, which is a gradient of 3. And so what we can see is that the graph is changing gradients as we move from different points, or the average gradients change with the different points. Okay, so let's make a more generalized situation from this. Okay, so I'm going to erase some of all this other stuff that I've just done. Let's just get rid of it here quickly. And let's see what we did in general. Okay, so being a function, we chose a point on this graph. Okay, let's choose a point. I'm just going to choose any random point, and let's choose it over here. Right, and this point has an x value, whatever the x value is. Now, when I plug that x value into the function over here, then I'll get a function value. I'll get a value for the function. Okay, So this would be the function value. And we could set up, instead of saying x and y, we could set up a whole series of values where we could plug in x values and get function values for the function. Okay, are you happy with that idea? So what I'm also going to do is I'm going to choose another point, and we know that this x point is a certain distance away from the first x point. Okay, we'll call this distance h. Okay, it doesn't matter what it is. In our previous graph, we made the value of h1, and we just went 1 unit up each time. We went from 0 to 1 to 2 to 3. So the difference in values was just 1. But let's just choose any random point and call it h. Okay, so this point over here has an x value called x plus h. Okay, but that means that its function value, whatever it is over here, would be the function of that x plus h. Now you'll remember from RG that we did this kind of substitution. We gave you functions where we said, okay, plug in and find the value. If this is f of x, what is f of a, or what is f of b? So here we've just got f of x plus h, so we're just going to put in x plus h into the function. Now here again, if we wanted to work out the gradient, which we could, the gradient would simply be as follows, and I'm going to just erase a few things here. And I'm just going to move this down a little bit as well. So if we had a function and we found its gradient, the gradient would be the function of x plus h value, that's our y basically, subtract the function of x. And at the bottom we'd have the change in x, which would just be the x plus h value minus the x. Okay, all right, well, we could simplify that a little bit further and say that that still equals the function of the x plus h value minus the function of x. It's just the gradient still. And what is x plus h minus x? Well, that's just h. So we end up with this. Now, we might say, well, that gives us the average gradient. But what if we made h very small? Okay, so in other words, we got closer and closer to this point of x, but we didn't just get there. So we just made x get smaller and smaller and smaller. And again, how small is small? Well, we can make it infinitesimally small. In other words, we can approach infinitely small, okay? Infinitely small, but not get there. Because remember, if we actually get to x, then we're just going to have x minus x, which is 0, and we can't divide by 0, so we can't have that at the bottom. But we just make h very, very small. Would eventually get a value, okay, which would be, for all intents and purposes, the gradient at the point x. And if we were just touching there, okay, we were very, very close, we'd have a tangent. So what we did just now was just find the average gradients, but now we're still finding the average gradient, but we're making those points so close to each other that for all intents and purposes, they are just about the same point. And therefore, we're actually getting the point or the gradient of a tangent at a point. So we can express this a little bit further mathematically by saying the following. Okay, so we want to know what is the limit as h approaches 0 of this gradient formula that we've just worked out, which is f of x plus h minus f of x. Remember, this is just the gradient all over h. It's basically the change in y over the change in x for this graph that we've just drawn here. But we've done it in general terms with two x values, one slightly set apart from the first x value by a small distance h, and then their two corresponding function values or y values when we plug those into the function. Okay, now this formula that I've just given you is probably one of the most important mathematical ideas that was ever developed. And this is a process that we're going to call finding the gradient from first principles, okay, or the gradient function from first principles. Because what we can see is that the gradient is changing for this graph, this parabola that I drew, the x squared minus 2. And I'm going to now do a couple of examples to show you how or what the gradient is changing like. Okay, we can work out this change of gradient for almost any function we like, and we're going to do that over the next few months with a whole lot of functions. So let me go down this side now. Okay, and I'm going to start with a simple function, and we'll make it even simpler than the one we had. I'm just going to draw the small version of the graph here, but this is x squared, a parabola that goes through 0. Now we want to know what is the gradient of this function, and we're going to use that formula that we just developed, because that is a gradient formula, just like change in y over change in x for a straight line, but this is for any function. Okay, and so what did we say that this formula was? Well, it was f of x plus h minus f of x all over h. Okay, and now let's plug in our function, because what is our function? It is x squared. Now if we plugged x plus h into this function, we would have x plus h all squared, correct? And then we just got to plug in x, which just gives us x squared and all over h. Remember, we still have the limit as h approaches 0. We won't apply that quite yet, but let's multiply out the bracket x plus h squared. What do we get there? Okay, well, I'm just going to move across a little bit again, and we'll just carry on over here. Okay, there we go. So what is x plus h squared? Well, that is simply x squared plus 2xh plus h squared, and then we've got minus x squared all over h. And remember, this is still the limit as h approaches 0. Now, therefore, we can call this, we can say it's equal to, what's x squared minus x squared? Well, that disappears. So we are left with 2xh plus h squared all over h, and of course the limit as h approaches 0. You're going to see why this is important in a moment. Now, at the top, I can factorize h out, and so I'm going to get the following. I'm going to erase over here a little bit, and we'll go back to this side. Right, and so we have the limit as h approaches 0 of h factorized out with 2x plus h all over h. Well, this means that these two h's can cancel, and so now we are just left with the limit as h approaches 0 of 2x plus h. Now, of course, this is the point where we're going to apply this limit, because 2x plus h, okay, if h is very close to 0, adding h onto that 2x makes very little difference to the 2x. Think of the value, for example, 2, okay, or let's say if I gave you 2 rand, okay, and then I said to you, well, I'm going to give you 2 rand, but I'm going to give to Connor a little bit more. I'm going to give to Connor 2 rand plus 0.000000000001 cents. Do you think that Connor would feel like he had gotten a whole lot more than you had? Or would you feel cheated by the fact that I gave Connor more than I gave you? You wouldn't really care, because at the end of the day, Connor's basically still got 2 rand. He can do nothing with the 0.00000001 cents. Possibly can't do much with the 2 rand either, but let's not get into that. Okay, but it's not a whole big difference. It's so little. So this is what we're saying. We're going to say that this h, which is so close to 0, is almost negligible. So basically what we can do, we're just going to ignore it. Who cares about it? Doesn't really matter. So what we then have, once we apply this limit over here, is we say that the answer is now simply just 2x. Okay, and then we can take that limit sign away, because we've applied the limit to the h. It means that the h is just going to be 0 or very close to 0, and therefore doesn't really matter within the sum. And so we're left with 2xx. Okay, and this is the answer to the gradient of the x squared function. So what we're saying is, if I want to say here is a function x squared, then the gradient of this function is 2x, which is still a function. What this means, okay, is if we look at the graph and we say, okay, let's plug in a value for x. Let's look on this graph. Let's take 1. Okay, if I plug in 1 into this gradient function that I've worked out, I get 2 times 1, which is 2. That means that at this point 1, a straight line that just touches at the point 1 will have a gradient of 2. And then if I take 2, for example, there's x equals 2. Then if I drew a straight line tangent that just touches at the point 2, the gradient of that line would be 2 times 2, which would be 4. And if I went to 3, okay, and I said, what is the tangent that just touches at 3? And you would get a gradient of 6. So we can see that the gradient is changing along that curve all the time. By the same token, if I took a value as -1 over here, then a line that just touches at -1 on that curve would have a gradient of -2. And you can see, look at that straight line. It does. It has a gradient of about -2. So we are finding the gradient, or we can tell what the gradient is at any point along the curve. At any point along the curve, for a curve now that is no longer a straight line. And we can do this for any curve we like. Okay. Now you might say, well, that's a very long way of doing this. Okay, and yes, I agree, first principles is a very long way to do it, but we're not just going to do first principles all the time. We're going to actually find a very quick method for doing this. However, before we get there, I'm going to do another graph, and we're going to look at its gradient function from the perspective of the first principles. So let's just clear everything away here quickly. There we go, it's all gone. And let's choose a function which you've probably seen before. And so here it is. F of x is equal to, let's do x cubed. Now, what does an x cubed graph look like? Do you remember? Well, the graph does something like this. Okay, it does something like that. Okay, so now we want to work out what is the gradient function along this curve. In other words, if I pick any points along this curve, what would be the gradient of a straight line that touches just at that point? So if I said to you at 1 over here, what is this gradient of this tangent? And maybe at -3 over here, what is the gradient of that tangent? Okay, let's go and see if we can work it out. Well, we'll start with our first principles idea again, which said that the gradient is defined as the limit as h approaches 0 of the function of x plus h, which is just a little distance away from x, minus the function of x. Remember, that was what got us the tangent, and it was x plus h minus x at the bottom, which is just h. Okay, so let's go and fill in the values here. Well, what is x cubed? Okay, so this means that we actually want to find x plus h cubed, because we're going to firstly plug in x plus h into the x cubed function, and then we're going to plug in x into the x cubed function, which just means we've got x cubed, and we're going to put that all over h, and we've still got our limit as h approaches, h approaches 0. Okay, all right, so can we work out what x cubed is? Okay, all right, I'm just going to actually go a little bit higher again. Or let's just come down here, and we'll carry on down here. Right, so x plus h cubed, so we've still got limit as h approaches 0, and x plus h cubed is simply x cubed plus 3x squared h plus 3xh squared and plus h cubed. Yes, and of course we're going to subtract the x cubed afterwards, and we've still got h. And we can say that this then equals the limit as h approaches 0, and the x cubed will disappear, and we're left with 3x squared h plus 3xh squared plus h cubed all over h. And again, we've got h everywhere on top now, so we can factorize an h out. So we'll do that, and we'll say this is the limit as h approaches 0 of h 3x squared plus 3xh plus h squared all over h. And of course the h's will cancel, which now leaves us with, and let me erase a little bit now. I'm just going to erase over here so that I can write a little bit more still. Carrying on from that bottom line now, we will say the following. So this is the limit as h approaches 0 of simply 3x squared, 3x squared plus 3xh and plus h squared. And now, of course, we can apply this h approaches 0 idea. So again, here I'll only then be left with 3x squared. That'll be my answer. Because the 3x times the h, if the h is very, very small, it's going to make anything that multiplies to it also very, very small. And so we can ignore it. And of course, if this is very, very small as well, when it's squared, it's even smaller. So it's also negligible. So the only thing that's going to have any effect on our graph or of our gradient is this 3x squared. So there we have an answer for the gradient of the x cubed curve. Okay, and that means, and if you look at this graph, well, we saw earlier, we saw that there is only ever going to be tangents along here that are positive. You see, all the tangents that we draw to this graph are always positive. The more negative values we get, so for example, if we put in a minus 4 over here into the 3x squared, the gradient function, minus 4 squared is positive 16, 3 times 16 is 48, so that would have a positive gradient of 48 at minus 4. But there'd never be a negative gradient because of the squared value of this function. Now, let's go to some more terminology. Okay, so what we do is we say that if we have a function, and again I'm just going to delete everything here. Right, so if we have a function, whatever that function is, and we calculate using first principles, that's the limit thing, the limit as h approaches 0, we find what we call the gradient function, and we're going to mark that like this: f prime x, the gradient function. And the gradient function will tell us the value of a tangent, straight line, tangent's gradient at any point along the curve. So we can now work out the gradient of a tangent at any point along a curve. Along any curve, doesn't matter what that curve is. Okay. And this is what we call the process of differentiation. So differentiation is finding a gradient function for any curve or for any function. Doesn't matter what that curve is. It can be x squared, x cubed minus 4, x to the 4 minus 2x squared plus 3x plus 10. It doesn't matter. Whatever function we want, we can now find a gradient value for a point along that function as a tangent's value, okay, or as the gradient of a tangent. Okay, so that's really setting us up for what differentiation is. In the next video, we're going to have a little bit of a look at how we can find different values for gradients and why this is important, and we're also going to find a quick method for doing that, but I'll do that in a moment.